to everyone for joining us today. I was looking at the numbers. It's very impressive. 95 people. I don't think I've ever spoken to 95 people before. So this is really cool. Will this work? Guess I have to press that. Okay. So today, of course, we're talking to you about automation and data-driven plan quality. And we're going to break that down into four main subjects. So first, I'll just introduce the topic, and then we'll talk about automation of the manual process. And then we'll talk specifically about knowledge-based planning. And then Minsun will talk about automated plan checks and then quality assurance of these systems. And then we'll conclude. So what exactly do we mean when we talk about automation? Because automation can mean so many different things. And in the context of radiation oncology, we're talking about technologies and systems that are designed to reduce human intervention in various stages of the radiation therapy process. So this means that there's varying levels of automation, which we can consider on a scale from no automation to being fully automated. And so here I've just shown like a general radiation therapy workflow. And this is just an example of something that would be partially automated. So one particular section of this workflow is automated. This is going to be partially automated. And of course, if the entire thing is automated, it's a fully automated system. But what's important, I think, to highlight before we start is that no system is fully automated. So when we do talk about the different automated algorithms, we're never talking about a fully automated system. We're talking about different parts of the planning process that are automated. So why do we automate a process? For several different reasons. It standardizes the treatment planning process. So that can lead to consistent applications of protocols and techniques across different patients and different cases. This standardization helps to reduce the variability introduced by different human operators and decreases the likelihood of errors. And then automated systems are able to produce treatment plans that are equivalent or even superior quality compared to those created by the average planner. And that's because these plans that are made are independent of an individual planner's experience, skill level, or given time constraints. There's a number of different factors that, we can't really account for that go into creating a given plan. In a system, we kind of filter those out, and you can offer safe and consistent quality care for all patients and all sites. And then, of course, we're looking with these automated processes to not replace planners, but to free up time for some more standardized processes so that they can focus on more complex or unusual cases where the human expertise is actually critical. And then I guess in the future, automation could actually facilitate a higher throughput of treatment planning and allowing hospitals to have a higher throughput of patients as a consequence. So we are going to talk about various automation processes to improve plan quality because lots of algorithms already exist. So when we're talking about automating the manual treatment planning process, we're going to be talking about MCO or multi-objective optimization, the hyperparameter tuning approach, and then also expedited constrained hierarchical optimization, or known as ECHO. And then when we start to break down some of the other sections of this presentation, we'll talk about knowledge-based planning, and then we'll talk about data-driven predictive models and the predicting planning parameters, so the DVHs or 3D dose distributions. And then Minsun will discuss rule-based or probability-based automated plan checks. And then, of course, our quality assurance of these tools. So how exactly are we quantifying plan quality? So you have a plan, how are you going to tell if it's good or bad? And there's different ways of doing this. So we have our population-based scoring, and that's typically generated from the results of clinical trials and empirical data. And it's as the title implies, it's aggregate data that comes from an entire population. And so some of these are the IMAMI thresholds, Quantec, or known as the quantitative analysis of normal tissue effects in the clinic, And then we have high tech, which is the hyperfractionated treatment effects in the clinic. And these metrics, the population metrics, are particularly useful in standardizing care protocols and ensuring that all patients receive treatment that aligns with the best available clinical evidence. And then we have something that's more patient specific. So our patient specific scoring. So we have our data-driven methods. So that predicts dose or DVHs that are achievable. And that depends on the unique features of each patient. And it can rely on past planning experience. And then we have our first principle technique. So calculating the dose gradient around the target volume, and then knowledge-based DVH prediction and deep learning 3D dose prediction. So both are important. Both population and patient-specific scoring are important. The population-based scoring is usually sort of like a baseline metric. Have you reached it? You know, typically like a typical value that would be something of high quality. And then, of course, the patient-specific scoring is going to be more specific to that patient's particular anatomy. So this is an example of an in-house solution that flagged a plan that actually did not pass the population-based metric. But if we actually look at the patient itself in the DVHs, this is the particular metric that did not pass the rectum. But if you look at sort of the scope or the range within which the DVH can land, it's on the lower end. So for this particular patient, it's this is a good plan. This is like an acceptable quality metric. So again, just to show that both metrics are important. And then here we have another sort of example of the clinical impact of data-driven plan quality control. So just to show that when you do implement some sort of standards for plan quality, it does make a significant clinical impact. So here we have relative excess dose to a parotid gland, and we have our basically the dose, that excess dose plotted over time, where in the red we have 3 months before the quality control was implemented, and then after, in the blue, after quality control was implemented, we can see that this excess dose was clearly reduced, dramatically so even. So I guess we can pause here just to ask a quick poll question. And this one is not a knowledge quiz. It's just, you know, we're curious. So is there automation used routinely in your clinic to improve plan quality?
Okay, I'm going to launch the poll. It should be available now. Looks like we have some answers coming in. So Stephanie and Minsun, maybe as people are answering, one question did come up in the chat, and it was, you know, sometimes if a patient has a treatment break, unplanned treatment break, you may want to add fractions at the end. Are you aware of any, you know, tools that would help, you know, with that type of decision making? I had to admit that I wasn't familiar myself.
Yeah, I'm not familiar myself either. So perhaps Minsun, you've heard of something.
Yeah, I'm not aware of the commercial, kind of a software to automatically calculate that, but sometimes we just compute this BED calculation, with the break in the middle. So, but that's somewhat like ad hoc. So I don't know. Maybe Ben can. What do you do when as a physician?
When we need to calculate additive fractions?
Yeah, like there's a treatment break in the middle of the course.
There's formulas for what you do to account for treatment interruptions that depend on a couple factors, like what histology is it? Is it a squamous cell cancer in the head and neck or cervix, or is it a slower growing cancer like breast? And then you plug in like how many days it's delayed and how many days you're in. And I've made a spreadsheet that has that calculator to make it easy to apply. Yeah. And so I can share that. I'll share that link in the group, and the results that you get, sometimes they make sense, but you have to be careful because the formula is not perfect. And sometimes it gives you an answer that is telling you you need to give more than the prescription dose. So that's definitely wrong. So in the spreadsheet, it turns red if it gives you a nonsense answer. I'll share that.
Great, thanks, Ben. And it looks like I think we've done with the poll, so I'm going to end it and share. So it looks like a mix of answers here, Stephanie.
Yeah, this is really interesting. So it looks like the majority of clinics do not have any automation. So I'm glad we're doing this presentation to sort of break down some of the possibilities. And then it looks like some for plan check only, and then some for generating treatment planning only, and yes for both. Okay, very cool. Thanks for sharing. Do I just close it?
I think I closed it. Is it closed
Oh,
now?
I guess it was just on my screen then.
Can you share results?
I did, and then I thought I stopped sharing.
Oh, okay.
I think we should be good now.
So yeah, so we'll talk first about the automation of the manual planning process. So first we'll talk a little bit about MCO. So a lot of people would know this, as the name implies, as an optimization algorithm. And we've included here because it is, but it offers the ability to be able to see individual planning goals realized, and in effect can give you an idea of sort of your best achievable plan quality. So the way that it works is that it takes as an input a number of constraints and then sort of like a wish list of objectives. And what it does is it takes those and it creates a set of what's called Pareto optimal plans to make up what's called the Pareto surface. And so it'll go through and it'll sort of optimize for an individual objective, having made sure that at every single point, all of the plans meet all of the constraints. So what you get is you get a series of plans. Each of them are optimized for a particular objective. And then and all of those create the Pareto surface. And then you can essentially scroll in between this Pareto surface. So you can sort of balance out these objectives. And a pro for the planner is then, of course, you can directly visualize the trade-offs between competing clinical objectives. And then a con for the planner is that it is computationally expensive and time consuming, and it does require prior knowledge of what optimal might look like. So yeah, depending on what type of plan it is, you might be running it overnight. For example, if it's a particularly complicated plan and you're going to need a good idea of what your constraints and objectives should look like before you run it overnight, because you probably as a planner don't have time to be running it, several nights in a row. So that's the con. And this is an example of MCO, what it looks like essentially. So we have our dose distribution in the far right that you can scroll through, a 3D dose distribution. And then next to it, you can see your DVHs. And then on the far left, you can see the sliders that we're talking about. So this is a particular objective that someone has put in. Like, I want the cord to be less than this, or to have this maximum dose. And then you can slide back and forth on how strongly you feel about that objective, or how strongly you need it to be emphasized in the plan. And then this is implemented in the commercial TPS. So we have RayStation primarily, and then Eclipse also integrated it in 2019. They integrated it into their system. So then the other thing that RayStation can do is it can create multiple plans. So it can generate plans for different machines as a fallback planning method. So that's another pro, I guess, of using RayStation MCO. So then we have ECHO, or the Expedited Constrained Hierarchical Optimization. So this was created at MSK, and the method organizes treatment objectives into a sequence of priority-based layers or tiers. And then ECHO starts with hard constraints that are essential for patient safety, and then it sequentially integrates softer goals to refine the plan. all along sort of ensuring critical requirements are met before optimizing. And it sounds like I'm describing MCO, but it is different in that it is more automated than MCO, where MCO still requires a significant planner interaction with the sliders. This method is faster, and it also reduces the dependence on a given planner's skill and time because, again, it's more automated. And then this is in contrast to a conventional optimization approach, where it optimizes all structures at once and then iteratively modifies priorities and objectives. So it's been used clinically for paraspinal bony mets, some prostate fractionations, SBRT lung, and then also some head and neck plans. So in the figure on the right, what you can see is the comparison of 25 SBRT plans that are echo generated versus the manual plans. So you can see that the PTV is generally more consistently covered with the echo plans versus the manual plans. And then the Paddock index, which is a conformity index. And you can see then that the echo plans are generally more conformal. So the blue line is higher in both instances. And then the plot on the bottom shows like dose to organs, like the relative difference in dose to specific organs for every single given treatment plan. And so, yeah, in general, echo is performing better. I'm not sure why, but it doesn't seem to perform better when it comes to the skin. But for the other organs, so such as the esophagus, it performs significantly better. So the pro for the planner for echo is that all of the steps of iterating with the optimizer are eliminated, and you can work on something else while echo does the optimization. And then the con is that it can't be applied for a case with a non-standard prescription. So the note there just being that if a couple dose constraints are different, that's okay, and it can be adjusted for. So then we have something called the hyperparameter tuning approach. So hyperparameters in our context would include something like the weights assigned to different planning objectives, like tumor coverage or OAR sparing, and then something like dose uniformity or conformity. And then the hyperparameter tuning approach uses advanced optimization techniques to systematically determine the best parameter settings for treatment planning. So it determines the best parameters that you then use for your planning. And then that's the core idea. So instead of asking the planner to sort of do a trial and error method and an iterative tweaking of parameters, it sort of jumps ahead, estimates based on the model what your ideal parameters would be, and then you can then fast track the process. So there are two primary methods for hyperparameter tuning. So we have random sampling, and that randomly selects values for hyperparameters within a defined range, and then it evaluates the resulting plan quality. And then we have Bayesian optimization, which is a little bit more of a sophisticated approach. It builds a probabilistic model of the objective function and then uses it to make educated guesses about where in the parameter space to sample next. And then the algorithm iteratively adjusts hyperparameters until it converges. And then the output is a set of hyperparameters that are theoretically optimal for achieving the desired balance in your treatment plan. So here we have an example or some results from a paper, and they are ROI doses for the clinical, randomized, and Bayesian plans. So that's the blue, orange, and green. And they're expressed in the percent difference from their clinical goal values. So each of these violin shapes includes a box and whisker plot, and that indicates the data quartiles. But essentially what we're seeing here, the OAR doses are better spared than the manual plans. And so the overall pro for the planner is that there's no manual intervention. The planner's time can be used more efficiently, and then it can be applied to a case with arbitrary or non-standard clinical goals. And then the con being that if the plan quality definition differs from what it was entered into the algorithm, you may need to re-optimize the outcome plan, and then it may take longer than KBP, which we'll talk about next. So just a couple poll questions. So first, which automation tool allows for the interactive exploration of trade-offs between different planning objectives?
Okay, let me launch that. Poll should be available. And maybe while people are answering the poll, there were a couple questions in the chat. One had to do with multi-criteria optimization and whether it's something that comes as part of buying Clips or RayStation, I think you mentioned, or if it has to be purchased separately. I think in Eclipse it has to be purchased separately. I'm not sure about RayStation.
RayStation, it comes with it. MCO comes with it.
Okay. And the question I had is because when I learned about MCO initially, kind of the selling point was it would give the physician a lot more control on their side to kind of choose what the plan, that they like the best is without iterating a lot with the planner. Just curious if you've used those tools, if that's kind of the reality that you've experienced. Is there more interactivity of the physician with the treatment plans than maybe with other methods?
Not that I've experienced, I don't think so.
Yeah, I mean, from my experience, no, not really, because MCO, at least with RayStation, we didn't actually find it useful for SBRT, case where high dose, a steep dose gradient is required. So it's more for the kind of a homogeneous plan, just a non-SBRT. That's kind of must be the built-in optimization algorithm within the RayStation, how it was implemented, the algorithm. But typically, yeah, the physician doesn't play with that trade-off. It's more for the dosimetrist, the planner kind of plays with the trade-off, and then they know what the physician wants, so that they just give that plan to the physician, present that to the physician.
Yeah, some of the objectives that are very common are not necessarily sort of intuitive objectives for a physician. So it'll be a certain constraint on a ring that they've placed around a target. And so it's not necessarily always the most intuitive in terms of it still requires some knowledge of the optimization algorithm and the planning process that may not necessarily be obvious, I think, to a physician. I like it. I like MCO. I like the ability to slide the bars. I think it's useful to sort of see the limits of a given objective, but it is very time consuming. That's definitely true.
Great. I think I just shared the poll results. So I don't know if you have any comments.
Well, so the answer to this question is number 2. It's MCO. And yes, so looks like a good number of people got it correct. But yeah, I suppose for those who, may have missed it, the other algorithms don't quite work the same way. So MCO is the only one that allows for sort of that slider bar between the trade-offs that you've specified at the beginning. The hyperparameter tuning is used to get, it's more of a forward planning type use where you use it to get the optimal parameters, and then you put the parameters in, and you can do that for standard opt. And then Echo, from what I understand, it's also it's more optimized, or it's more automated. So there's less planner interaction with the algorithm. So yeah, MCO is the only one that allows you to slide between the bars there.
Just to add the context, the outcome of the hyperparameter tuning and Echo is one plan, single plan. So it comes outputs one plan, whereas MCO actually outputs a bunch of Pareto optimal plans on the Pareto surface, which means that none of the plan is superior to another. That's what basically Pareto optimal plans. So it's one plan is better in one objective and the other plan is better on another objective. So that's why you cannot really compare superiority between the plans. So that's Pareto plans. So that's why there are a lot of Pareto plans, so that clinician can choose what they want.
think I closed down the poll, hopefully.
So we have another question. Are we doing okay on time? Should we?
I think
Skip
we're
over this
doing
question.
okay.
Okay.
I think
Okay.
we'll-
So then what do we think is the primary goal of hyperparameter tuning approach for automated planning?
Okay, should be launched. And I think Jose had a question about this approach as well. Maybe since it's in the poll question here. And I guess Minsun's probably the best to answer this. Does the algorithm need to be trained with clinical cases, or was it trained with a standard data set? And if it's a standard one, where did that data come from?
So the benefit of hyperparameter tuning does not require a large data set. So it doesn't require the predictive model. So that's kind of one of the benefits. So there's no training set. It's just a different algorithm, just like the echo. The echo is not requiring predictive model either, right, John?
No, no.
Yeah.
Okay, I'm gonna end this poll here. Share the results.
Okay, so most people guessed number 3. And Minsun, yes, that is the correct answer. So yeah, so to reduce the overall treatment planning time and improve plan quality beyond human intuition. So good job, everyone.
Okay, it should be closed.
Okay, so now we can move on to knowledge-based treatment planning. So what exactly is knowledge-based treatment planning? So this method uses AI and statistical methods to improve the planning process. So in an AI-based solution, we have a model that learns characteristics of previously accepted plans to set planning parameters. So that's sort of a hallmark of it, is that it's using a large database of previously optimized treatment plans. So sort of an emphasis on that population-based planning. And this kind of planning process has been shown to increase efficiency and reliability above the current clinical practice. So we have, as we've talked about, there's a range of AI from more basic to something that's more complex, like neural network. So on the sort of more traditional, less complex side, we have like the traditional KBP. So the input to that kind of a model would be something like anatomical and geometrical features. So a classic one is distance to targets, different volumes, overlap, volume histogram. So those kind of metrics that are put into a model, what kinds of models are they? They're atlas-based, they're statistical modeling, they can be machine learning that's not a neural network. And then the output is objective function parameters. So for example, our DVH metrics, and then a dose distribution. So then if we look at something that's more deep learning based, we have our raw data as input to these models, because they're more complex. They can handle much more data. They don't need it broken down into features. So they actually take in the raw data and they can automatically detect image features. And so some of those images are something like CTs or dose maps, contours, etc. And then the models that are built are typically, as mentioned, neural networks. So ANNs, CNNs, UNet, ResNet. So all of those are neural network-based models, or deep learning-based models. And then the output from that can be a 2D or a 3D dose map. And then like in MCO, that Pareto optimal solution, a model like this can give you a Pareto optimal solution as well. So if we look at sort of the outputs, so this is from something like the more traditional KBP method, we have predicting of the dose volume histograms. So what would be the input for this? We would have the patient's anatomy and then the prescription dose to the target. And then the output here, we have predictions and achievable consistent DVH goals. So you can see in the far right here, we have the different anatomical structures. So in the blue, for example, we have the rectum, and then we have a shaded area within which is sort of the suggested range for the DVH to land. And in this case, actually, maybe Minsun, I remember we talked about what these arrows mean for this particular example, but maybe you could clarify.
I think that that's the best achievable,
Okay,
so that those points can be used as an input for planning.
So then we have some dose volume histogram error types. So we have so we've got A and B, so we've got type 1 and type 2. So type 1 is when your planned DVH is falling below the best DVH and then above the overestimated achievable DVH. And the clinical consequences of something like that is that your OAR is overspared, and that you've actually made the wrong trade-off where the competing objective is undetermined, and then the clinician, I suppose, is confounded. And then we have our type 2 DVH estimation error, where the resultant plan DVH is very similar to this underestimated achievable DVH. So it's pretty much exactly the same. And then we have it way above this best DVH on the bottom here, where the clinical consequences of this are that the OAR is, of course, underspared, and the clinician may not actually detect this error. So this is just to show that the type 1 DVH estimation error is easier to detect than this type 2 DVH estimation error. So then we have our 3D dose distributions. So we, as mentioned, we get either DVH metrics or our DVH graphs, but that's not necessarily giving us 3D dose distributions. So we could use the deep learning models, as already discussed, to directly predict 3D dose distributions. And that's typically using a neural network that's been trained using, again, like a large amount of previous data. And we can use that to predict a given dose matrix based on the patient specific, that your input patient, based on their specific geometric and planning parameters. And it can be used for that direct voxel-based optimization, which is pretty amazing. So there are commercial solutions available for predicting the planning parameters. So for example, we have Rapid Plan here, and it's a PCA regression model, and it estimates DVHs using plan details. And what it outputs to you is upper and lower bounds of DVHs for the plan in question. So we had showed an image of this before, but what we're seeing here is a range within which, based on your plan, will search for plans that are similar, and it will give you a range of DVHs that it estimates that you should be able to fall within. And then it will actually show where your DVH is in that range, if it's in the range or outside of the range. And then we have another example, OncoSpace. So it also predicts ranges of achievable DVH metrics for a given patient's anatomy and uses the best achievable dose parameters for planning. And the main difference between OncoSpace and Rapid Plan is that OncoSpace is not connected to a specific vendor, so it's vendor neutral, whereas Rapid Plan is a variant product. So, but similar outputs. So, another poll question. What is the primary advantage of knowledge-based planning?
Okay, and the poll is launched. No questions came up kind of in the last few minutes, but I think, we do want to make sure that we're respectful of time. So once this poll is done, I think we may, this is actually a good question here to launch itself. So it looks like we have a couple more respondents coming in, then I'll share. Okay, here we go.
And then actually just a logistical question. So Minsun, would you like me to continue to advance the slides for you? Or would you like to share your screen instead?
Oh, either way is fine. We can just, For the interest of time, we can just go quickly.
So I think I shared the results of the poll, and it looks like a slim majority chose option number 2.
Correct. Excellent. I'm glad we are communicating effectively.
Righty. Is this when we're transitioning over to Minsun now?
Yes,
All right. Thank you, Stephanie, so much.
thank you.
Okay, so for the next kind of half of the talk, I'll be talking about the automated plan checks. So, as a physicist, we're checking the plans, and then, if you want to really catch all the high quality or versus the, acceptable quality, or even the errors, it takes a lot of time. So what kind of a tool can help us reduce the time that we spend on plan checking? So that's what I'm going to talk about. So what type of plan check can be automated? So obviously not every single thing that we do as a physicist to check plans is automatable. So some of the examples of the scriptable checks are shown here. So we talk about during the disease site-specific plan check lectures, we learn about the technical aspects and the clinical aspects that we are supposed to check to make sure that the plan is the high quality. So technical aspects, beam configuration, the number of arcs, so all those things are very easy to automate. How many arcs are there, whether the clearance is okay, or what kind of collimator angles, and there's no, same collimator angle for the VMAP plans and so on. So those are easy. Plan modulation, if you're talking about the modulation factor, which is the total MU per fractional dose, is also easy to automate. Treatment devices and the density overrides, whether the bolus was included and the metal override is included. So all those things can be automated. But what's not easy to automate is, optimization objective priorities. So which one it has a higher priority, the relative weight between the competing objectives, clinical objectives. That one is very hard to automate, as you can imagine. It's very patient specific, and that's another thing. So from the clinical aspects, registration is very hard to automate. But I think people are working on quantifying the quality of the registration. So I'm not sure if any of you is aware of the commercial software to compute the quality of the registration yet. I know that a lot of research is going on in that aspect, but so at this time, it's not trivial to automate the quality of the image registration. But then, there are other clinical aspects that we can automate, images, the check sim date and scan protocol, whether those are correct or not. Okay, next. So, how much time saving can we do with the automated plan check? So, why do we care about the time when we talk about the plan quality? So obviously, when we reduce time to spend for plan checking, that time can be used for something else, like a checking plan quality. So they are somewhat related, not directly, but indirectly it's related. So Sean actually did a study for this so that they reported 10-minute time saving per patient by using the automated plan check script. So that is a 20% decrease in plan checking time. And another study actually shows that 60% reduction in patient delays due to treatment management system or the treatment planning system errors in the 6 months after they implement the automation plan check tool. So next. So I want to talk about what kind of plan checking tool is available. So, there are various metrics for quantifying plan quality. So there is a simply rule-based and then probability-based. So what is the rule-based? So rule-based actually requires the expert's knowledge is in what is good and what is not. So you have to know what kind of rule you want to apply. So based on that knowledge, you have to set up the rules. It's a pretty simple. So for example, if there's a pacemaker, then the energy has to be 6 MV to reduce that neutron dose. And then if it's a VMAT, then plan modulation factor is less than 5 or 6. So whatever the institutional consensus is. So minimum MU per segment is another criteria that you can actually check based on the rule base. So those are simple things. It's very easy to implement, and you can actually script it pretty quickly. But a little bit more sophisticated one is a probability based. So it can detect the errors using a probabilistic network. So you don't know it's like 100% correct or 100% wrong, but it actually gives you the probability of being right. So, oh, if it's 80% of being right, then okay, so it's right. But then if it's a 20%, then it's an alert. So you have to actually set the threshold on at what point you want to actually double check, at what point it actually requires human intervention. So the Bayesian model or even deep learning model recently has been used in the research paper. So one of the Bayesian model is the conditional probability, so that basically I'm going to actually show that example in the next slide. But for the given tumor type and treatment intent, whether it's a palliative or cure, the likelihood of the prescription dose is correct. What is the likelihood of the prescription? So if it's a palliative, for example, like a 3,000 centigrade in 10 fraction, I mean, that is probably everybody recognizes that is a pretty good dose or a common dose fractionation for palliative. But then if it's used for curative intent, then the probability of being correct is probably low. So that's how that Bayesian model works. And then recently, there's another report that used the deep learning model. And based on the MLC positions in the plan, heat maps are generated. And then it actually determines if the given plan is consistent with its intended use, which is actually the correct the treatment site. So whether it's a right arm, and then if it was a plan on the right arm, something like that. So that's what they use. So this is the in-house solution at the University of Washington. So it's a plan check tool that uses both rule-based and probability-based Bayesian. So it was developed in R language, and then also web browser interface, so that it's very easy to use. You can select a patient, as you can see here, and then prescription, and then there's a bunch of tabs, and then I highlighted 2 of them in the middle, which is the rule check results and then probabilistic results. So the rule-based check is actually shown here. You can see that deem those checks, set up energy check, prescription not approved. So all those things, whether it's a pass or fail, based on the rules previously entered. And then next. So the next one is the probability Bayesian based plan checks. So now you can see that it actually gives you the probability. And then I think we internally set that 2% or, yeah, so you can see the yellow, green, and red. So if the probability is lower than the threshold, then it shows red. And then if it's a warning yellow, so it's a certain probability, then it becomes a yellow. And then anything higher than certain probability, I forgot what it was, 50% maybe, or 20%, then it becomes a green, so that it is you can visualize the probability of being correct. So one example is the, total dose and fractionation. So for that given disease size, stage, and intent, whether it's likely to be correct or not. And then planning technique is full arc versus partial arc. If the tumor is located laterally, then it's more likely that partial arc is actually should be used. And then if it's centrally located, then more likely the full arc should be used. So that's kind of a probability that you're aiming for. So there are a lot of resources of automated checkers. So if any of you is interested, I can actually connect you with those in-house script checkers, because they are willing to share. I'm not sure if everybody actually has it in the GitHub, but some of the example institution developed checkers are very useful. So Ray Station, so University of Washington has it, and then also the University of Wisconsin Medicine and North Carolina has the Ray Station based automated plan checkers. And Eclipse plan checkers are available at University of Michigan, UT Southwestern, UAB, and then MSK, as far as I know. But there are a lot of in-house kind of developed plan checkers available. If you can also go online for GitHub or webinars is another source that you can find. But please feel free to let us know if you are interested in trying any of the in-house automated plan checkers. So this is the poll question. So which of the following cannot be checked by a rule-based automated plan checker? Can you launch the poll, Sean?
It should be available now. And there was some discussion in the chat, but I think we've taken care of it. So again, just for the sake of time, I think we'll just focus on the poll question here.
Okay, so this is cannot be checked by a rule-based.
Looks like we have about a third of the people have answered so far. Okay, the responses are slowing down, so I think I will just end here and I'll let you respond.
Okay, so I guess it's somewhat equally split. So yeah, it is a little bit foreign concept if you're not used to it. So the answer is actually prescription dose and fractionation is appropriate for the disease site, stage, and intent. Because the rule-based plan checker actually needs a set rule. If it's a this, then it should be that. So it's a kind of a defined logic. It follows the predefined logic. So that prescription dose and fractionation it's hard to actually define. It's always this way. If it's a disease site, this stage, that intent, that, and it has to be always this prescription dose and fractionation. It's not like that in medicine. So it's always can be estimated as a probability. So now we are going to talk about the last section of the quality assurance of automation and the data-driven plan quality tools. So, as a physicist, it is always our priority to make sure that whatever we use in the clinic and for the patient is safe. So quality assurance is the essential part of all those somewhat black box. So this key knowledge-based planning or automation, is somewhat like a black box, right? So we don't know what's going on because unless you actually develop one at your institution, but then even then, unless you're a developer, themselves, it's very hard to know what's going on in the black box. So the QA, I think, is actually very important. So let's see what we can do to make sure the device or tool is safe. So before we do that, how often do you QA automation tools if you have one? I know it's a lot of you, actually, the majority of you had some kind of automation tools from the previous poll. So it's a one-time or annual or more often or no regular schedule.
This question made me think when I saw it before. I said, I wonder.
Yeah, how often do you QA?
Yeah.
Okay.
I mean, so we focus I focus on our plan check tool, and I guess I have to admit we don't have like an annual QA process, but we are constantly rolling out new versions. So there's a lot of testing.
I see. Yeah, I mean, that is kind of some kind of a test.
Evaluation, yeah.
Should we end?
Okay.
Wow. So, I mean, it's either we don't use automated tools, which is understandable, but then once you have an automation tool, a lot of people do the periodic QA more than once a year. So that's good to know. So let's see what kind of a QA we could do. So a lot of times, like a lot of a QA is done upfront. It's heavily loaded, before you introduce that tool into your clinic. Can we go to next? So I want to talk about so most of the QA tools published is the AAPM task group report 308, which it hasn't been published yet. It's forthcoming. So it's about the clinical implementation of data-driven quality control and automated treatment planning. So this report is the recommendation for data requirements for modeling training sets and planning libraries. So the modeling training sets is the kind of essential part of the KBP. So what kind of data is needed, and also how to analyze those estimation accuracy and quantify model errors. And then it also have some recommendation for quality assurance of the training sets and preclinical validation of automated planning routines, and then also the clinical implementation. So we're going to actually go over this in details. So we can just move to the next slide. The overall process of implementing predictive models into clinics. So this is the black box part for the knowledge-based planning. So predictive model, you can either build your own model or you can borrow a trained model. So we'll talk about briefly, how to build a model. So you have to select the case and then, what kind of a data you want to include and how to label each data set. And then also how to train the model and then how to evaluate the model. So we're going to talk about actually a little bit more details, those building a model in the next slide. So, but a lot of institutions do not have human resources to build a model. So it requires expertise that not all medical physicists are trained to have. Or, simply the clinic is very busy so that they don't have enough time to devote their time to build a model. So in that case, you can actually borrow a trained model. So Orbit RT is actually kind of a open software that it's a website that you can go to. It's developed by the UC San Diego. So they actually offer, I don't know how many, but a lot of predictive models for many different kinds of disease sites for the Eclipse system. So you can download and then you can actually use that. But even if you use this model, you have to understand, the scope of the model it was developed for. So what should you do when you actually borrow somebody else's model? You have to understand contours and dose for fraction, and then training set, plan quality. So all these things, we're gonna talk about that. So once you have a model, then you have to validate the model. So obviously, when you do the model validation, you have to use the independent data from what was used for training. And you also have to validate your own clinic. Every clinic may have different patient population. So you have to validate in the data that represent the range of patient geometries or plan techniques, prescription that you use in your own clinic. And the evaluation of the quality of a plan generated by the model. So you also have to confirm, yourself that how the plan quality comes out from the model. And then once you like the model, then you have to implement in the clinic. So you have to develop the guideline for clinical use and define the scope of clinical cases validated. So you may realize during the validation, this model is not appropriate for, certain type of patients, maybe for large patients or very small patients, so whatever you find, you have to actually put that in the guideline. Standardization protocol, so the contour, beam arrangement, plan evaluation metrics. So it's all related what was used in the training set. Next. So this is training data process overview. So you start with the patient selection. So first you have to include some n number of patients. And initial model training is going to be done on that n number of patients. And then you actually identified outliers. So there is the geometric outliers and then also the symmetric outliers. So geometric outliers is the patient geometry that is actually out that is very different from the majority of the cases. And the symmetric outlier is the one that once the plan is generated, the symmetric, like a DBH or the dose, is very different from the majority of other patients with a similar geometry. So then those outliers are identified and removed so that the final training set will be less than the initial patient that you selected. So final model train is done, and then clinical knowledge-based model is created, and then the validation. So that's kind of an overview of the training data process. Next. So then what is the geometry and the contours in the training data set? So it includes the expected clinical range of target and OAR, volumes and distance, plus the overlap relationships of target with the OARs. So every clinic, may have a kind of a different patient populations, so different clinical range. So you want to avoid cases with anatomical features, that are very different from the normal range of a variation. So in the figure, you can see that for the prostate cancer, so the bar graph actually shows the prostate volume, and then 50 to 75 is just a little bit, and then the largest number falls into this between 100 and 125 cc. But then there is actually a patient whose prostate volume is over 350. So that's in the right arrow of the red arrow. So that those outlier, can actually distort the model, so that is actually identified as an outlier and then removed. So, but then if you look at the B and C, so there are both outliers, as you can see. They're actually far from the rest of the data set. However, in the B figure, that outlier does not really influence, because when you see the linear regression, it is actually on the same line, so that it is non-influential, so you can actually keep the data in the training data set. However, on the C, that outlier is actually different from, it actually can distort the model, so that outlier is considered as influential, and then that should be removed from the training set. Next. And then what about the plan quality? So that is based on the geometry, right? So, but then, once the plan is created, you will see this tumor dose and the OAR dose, and then, how much OAR sparing was done. So you want to avoid cases with the dose distribution outside the normal range. So it's just very similar to the anatomical outliers. And then, but what's important here is that if it's actually the outlier is more on the more sparing for the OAR, so it's a better, higher plan quality, you may actually want to keep that to just push the dose to the OAR. But definitely, if that outlier, is worse than the majority, the normal range, then you definitely want to throw that out, because you don't want to include the low quality plan in the training data set. So in that case, those kind of 3 outliers in the red circle, you can actually replan to get into the normal range, so that you want to include, because you have only a limited number of plans in the training data set. So instead of throwing that out, you can actually replan and then see if you can improve into the normal range. And then, so when you actually select the training data, so disease sites, so how specific you want to make the model for? Meaning that, is this model for any disease site, like, so general models, so say the head and neck. So is that actually, this model is for head and neck? Or is this model for nasopharynx, larynx? So very specific, within the head and neck. So which one is better? So the general model is simpler. It's just likely to handle larger variety of the cases. And then, but the potential downside is that, it may get larger variance in predictions because the data is more heterogeneous. So it is more applicable, but at the same time, variability could be larger. Where the specialized model is, it is good, maybe a smaller variance in predictions because it's very specific to certain disease site, very narrowly defined. But if it's too specialized, then it may be difficult to match clinical case to model. And then also the number of the plans in the training data set, it might be hard to get depending on how specialized it is. So in that case, you can have a multi-institutional development of the model so that you have more plans in the training data set. But the downside is that if the contour names or the data is not standardized, then it's hard to curate the data into the same model. But the study actually shows that it's a similar trade-off when considering the range of prescription doses and the range of target coverage or normal-tissue sparing trade-off and treatment technique. So if you consider all of these variability in the plan, then the general model versus specialized model, the trade-off is similar. So now how to validate the predictive models. So you can validate the closed loop and then open loop. So closed loop is validated model on training set. So obviously it is less. So yeah, so closed loop is so it is more likely that the model actually shows a pretty good plan because it was trained for that specific model. And then if you actually validate against what was trained, then you're going to have a good plan. So, but then, when you use that in the clinic for the new patient, you may not get results. So open loop is to validate the model on an independent validation set. So whenever available, that is actually recommended to validate open loop. So the number of plans in the validation set depends on, how complex the plan was, and then, so it is like as a specialized versus the general model, right? So general model is applicable to wider range of the plans so that in the validation set, you want to include a lot more plans to validate. Whereas if it's a specialized, if it's applicable to only certain, constraint, then the number of plans that meet that constraint could be, low. So if not available, but if there are not enough plans available, then you can design a pilot study, complete a full analysis for a subset of patients during the clinical implementation. And then, so you are actually validating as you go in the clinic because you don't have a lot of plans to validate upfront. So then you just design this pilot study. So you roll it out for, the real patient as you go. And then once you gain more experience, then you can actually roll it out to the larger patient population. So what's important is to confirm the appropriateness of the models in your own clinic. So, and then also the dose estimation performance on the out of sample validation data set should be equivalent to the estimation performance on the training sample.
So Minsun, I think we're getting a little tight on time, so maybe I would recommend just answering this question so we can,
Okay, so
I know there's only a
be,
couple of slides.
Yeah, used in the training set for KBP. So the plan that is an outlier symmetrically and then outlier geometrically, the plan where you expect a compromise between target coverage and OR sparing, the plan that is out of scope for the model. So it is the 3 because you always expect a compromise between the target coverage and OR sparing for most patient cases. So that's not considered as an outlier. That's actually considered as kind of in practice. So let's go. So another quality assurance, the evaluation metrics for various auto planning tools. So This is actually to assess the robustness of the auto planning tools by evaluating the changes in plan quality with respect to small variation in various planning parameters. So for example, like the placement of the isocenter in automated treatment planning. So if you actually change the placement of isocenter by a small amount, how does that affect the plan quality, the resultant plan quality? So those assessing the robustness is important. And then auto contouring quality evaluation can be done by dissimilarity coefficient test, which is actually shown in the figure on the top. And then also the Hausdorff distance test, which is the just greatest distance from a point in one set to a point in another set. So that is shown in the figure on the bottom. And then, so those are the quantitative metrics, and qualitative evaluation can be done by having the physicians rank the automatically generated plans. So see what physicians think is a better plan. So that's a qualitative evaluation. And it's important to establish the benchmarks using a set of standard cases to evaluate the consistency and reliability of the auto planning tool. And then I think it's one of the last slides, so that continuing education and training is obviously key to ensure the patient safety. So you have to understand the impact of auto planning only versus the auto planning and then manual tweaking, and then see which one is needed to ensure patient safety. Sometimes, just the 100% automated plan may not actually result in clinically acceptable plans, so that manual tweaking is necessary. So you have to test that for your own auto planning tool. And then also phased rollout among different treatment planners is another tactic that you can use, so that it don't roll it out to everyone at the same time. You start with a small group and then have them develop the expertise in auto planning, and then they can actually train other treatment planners. So this phased rollout is a good approach. And then you also definitely have to understand the applicability and limitation of the model. As you can see, the model may not be for every patient case. So you have to understand the limitation of the model. And whenever there are practice changes, so the clinical priority may change, or there's a new population-based protocol come out, so where those tolerance dose is different from what we used to think was the safe. So then you have to examine if the model can meet that new goals. So because the model is actually built with a very specific practice guideline, and then if the practice guideline has changed, then you have to evaluate if the model needs to change. And then periodic checks and reviews are necessary, so you can compare the plan against the benchmark plan, so that it actually produces consistent plan quality, over time.
So I think we're nearing the end of our time, Minsun. There's been a lot of questions in the chat that Stephanie and I have been working through. So definitely you've been getting a lot of interest in the talk. But again, probably with this one, I'd maybe recommend if we just move over it, and then in case there's other questions people want to ask.
So that,
that's a good idea.
Answer, and then I can actually
go over to the next.
I just want to know.
That's a great idea. Yep.
Yeah, what is the biggest challenge to implement the automation tool in your clinic?
Perfect.
So, so if one of Stephanie or Sean, if you can just copy and paste the answers in the chat so people can choose, I guess. Then
I launched the poll. As you're in the next slide, people can keep going. Yeah, that's a good idea.
Yeah, because that was actually my interest. I was wondering what challenge everyone has. So this is the last slide, conclusions. So I'm reiterating the importance or the caution that we have to consider. So automated treatment planning tool can reduce plan variability, leading to better quality control, plan quality control, And then not only that, it can also enhance plan quality by incorporating what is achievable for given patients. It is a personalized treatment plan that's optimal for that given patient. So additional time required to ensure plan quality beyond the minimum standard can be saved by utilizing automated tools for greater efficiency. So that's why, saving time is important, because even though it's not directly related to improving plan quality, but that resource can be utilized to make sure to improve the plan quality. Understanding the scope and limitation of automation tool is essential to maintain patient safety. And also the last, continuing education is the key. The technology is evolving, everything is changing rapidly in this field of medical physics and treatment planning. So staying current with the updates and changes is actually necessary and to ensure the patient safety. So thank you, everyone. So sorry that we just went over time.
I think it's just because we had a lot of good questions. Thank you so much. So a few things. I'm going to stop sharing the poll. I think I know I'm available. Maybe Minsun and Stephanie are available. So if there are questions, we can probably answer them. We just didn't want to hold people longer than they intended. And the other thing is that Ben said it might be nice if people were willing and able to turn on their cameras, and I'll take a couple screenshots just, to close out the class. So I'm going to share the results here. And if folks turn on their cameras who want to, as I see those cameras come on, once there's a bunch of them, I will take a couple of screenshots. But Minsun, including these challenges, there was a question in the chat that I was unable to answer, which was, does anyone have an idea of the approximate cost of some of these commercial tools? I said it probably depends on a lot of things. And, unfortunately, or fortunately, I'm not involved in purchasing myself. So I don't really have a great idea of the cost, but I don't know if you or Stephanie have different experience there.
Yeah, it really depends on, so like auto contouring. So it really depends on what you're interested in. It's kind of hard to generalize because there are so many different kinds of automation tools out there. So automated contouring is one of the more common automation tool available commercially. And then that really depends on the vendor. So, we have used the MIM so some of them comes with the software automatically, and then some of them is a separate purchase. So it is kind of hard to generalize. Yeah. But then again, like automated plan checkers are available in-house. So I'm sure that they're all kind of willing to share their in-house developed software. So that's freely available.
Okay. Do you have any comments on the poll? Am I still sharing the results?
Yeah, so I guess lack of human resources. So, that's always, that's a problem in the US as well as I see now globally. So, because I was wondering if they have kind of a different challenges compared to the US, but the majority is no automation tools available. And then the second is the lack of human resources. So, yeah, so the lack of human resources is common, between the US and globally. Looks like.
Always a challenge.
It's always a challenge. So that's why I think we need more automation so that it helps with the efficiency, right?
Yeah. And then the other question.
Sharing so that you can see
poll. Sure. I think the other question that I wasn't able to answer necessarily was there was a question about what automation tools are in Electa. I don't have that much familiarity. I don't know that you or Stephanie do either with their suite of tools there.
So you're talking about Electa Monaco treatment planning system?
Yeah.
So Monaco is actually, we do have a Monaco in the satellite. So I'm not using it on a daily basis, but in that clinic, we do much less automation than my clinic where we use RayStation. So RayStation has a lot of automation, kind of at least a scripting, in-house developed script can be used. But Monaco does not have a scripting interface. So the automation is a little limited from my observation.